that? What'd you say, Laura?
I understand that.
Okay, good.
Oh, I
Um,
understand that. Yeah.
good. All right. Well, let's take a look at just a little diagram that I like to draw at the beginning of class. Let me share my screen. Okay. I need to get my notes. Okay. All right. By the way, I should probably mention what the structure of the class is, right? We have homeworks. We'll have 2 take-home tests and a take-home final. That's kind of how it works. Okay?
Mhm.
All right. All right, I'm really bad at drawing, but I will try. So we're going to sort of look at a little diagram that's going to tell us all about physics. Um, and so I'm going to start with a little line here. I'm going to try. Yeah, well, here, I'll just start with this little corner. So I'm going to, up here, we're going to put classical physics. I'm going to actually put classical mechanics, which is really just another way of saying classical physics. Okay, so CM is classical mechanics. And this is the realm where everything's deterministic. Yeah, maybe you can't calculate everything because it's too hard, right? You need too big of a computer. But it's all deterministic. All right. Now this line is an axis, and along this axis, if we go down this axis, we get faster, right? So if we go down the axis, we get faster. And when we get to the faster area, right, we have something called special relativity, right, which you guys have learned in 251. So special relativity is actually part of classical physics, even though it is pretty weird, as you probably remember. Okay. But that affects things that are going fast, right? You don't notice special relativistic effects in your everyday life because you're not driving, down, the street at close to the speed of light, right? Um, okay. Now, if we go down, so we're going to go down here to small. So if we're this axis, we get smaller. If we go down here, and if you follow down this line, there's quantum mechanics, right? So when we get to the small, and again, you don't notice quantum mechanical effects in your everyday life because you are not a microscopic object. And although you interact with microscopic objects, you always interact with them in the aggregate, right? So yes, you are made up of microscopic objects like cells, but even those are pretty darn big compared to atoms and electrons, right? Anyway, so this is quantum mechanics. Now, I'm trying to make a cube. I'm really bad at drawing, but I'm going to try to make, so think of this as just part of a square. And maybe we should sort of complete the square a little bit. So I'm going to go down here. So now if I go down this axis, I am getting smaller, right? Because small is down this axis. So I'm fast and small. That is something called quantum field theory. And quantum field theory is something you never learn about. Almost, I don't know anyone who's learned, there's no undergraduate class ever in quantum field theory. It's always graduate level. And usually it's graduate level in like second or third year, not even the first year. Okay. Pretty hard stuff. Okay. Now, so we have sort of the square here a little bit, and I think I'll just sort of I'm not going to put this in, but because it's going to mess up my drawing. But okay. Now we're going to try to make a cube. So I'm the worst drawer in the world. So we're going to go to another axis that comes out of the board. So here's my attempt at making it look like it's coming out of the board. That's really bad. But along this axis, you're getting more massive. So you're adding mass to the system. Okay. And when we come out here, this is, now notice on this axis, so imagine this coming out of the board at you. This is, we haven't got we're not faster or smaller, right? We're just more massive. And this is just the realm of, regular old Newtonian gravity. So, big planets, big things, right? Newtonian gravity. And of course, Newtonian gravity works on small things too. Um, but for instance, you do not notice the gravitational attraction between your pen and the desk, except for, what you're noticing, of course, is the Newtonian attraction between your pen and the earth, right? But if you had your pen and your desk in space somewhere far from the earth, you probably wouldn't notice that they're attracted to each other. Of course they are, right? So you really only notice Newtonian gravity between large things, and we all notice it because we're on a very massive planet called Earth, right? That's why we notice it. Otherwise, we wouldn't notice it. If you and your pal were just off in space far from any planets, right, you would not notice that you were gravitationally attracted to each other. It's a very weak force. You just wouldn't notice. We have a lot of experience with Newtonian gravity because we're on a very big thing, right? Okay. So anyway, so here's but just the point here is if this is, these are deterministic. This one's deterministic. This one is deterministic. This one's not deterministic. Okay. Okay. So how was I gonna do this? Ooh, hold on. Move my screen. I didn't mean to. Okay. So now if we go out along the massive axis from here, so now we're going to be fast and massive. Again, you can see I'm a terrible drawer. So remember, this is the massive axis. Then we get to something that's called general relativity. And this is actually the true theory of gravity. So of course, Newtonian gravity is the gravity when, when things are, the sort of normal sized planets and stars, etc. There are general relativistic effects that you definitely measure in say orbit around the Earth, and we do measure them. But general relativity is sort of the true theory. Newtonian gravity is used because general relativity is exceedingly more complex to use, and it's unnecessary to use general relativity for things like, how fast does the pen fall when you drop it? Okay. You just don't need that. But the true theory of gravity is general relativity. Okay. And this is deterministic. Okay. Now you might think, there's some axes off that are left off this thing, or not axes, but points that are left off, right? Because if we had a cube, it would be, down like this, right? And again, the worst drawing ever. Okay, so what are at these points here? Sorry, sort of looks like a cube, maybe. Okay, so what are at these points? Well, here, this is the intersection of things that are massive and small. Here, they are massive and small. Did anyone think of something that is massive and small? And by massive, I mean, like a solar mass. Any ideas?
You said massive as in a solar mass?
Yeah, well, as in like a solar mass. That's what I mean by
Hmm.
massive. Big.
Mhm. Um, well, let's see. So, I don't know. This may be completely off, but
Okay.
both big and small, I think of like black holes or
Yeah,
wormholes or something like that.
absolutely. Yep. So when I say small, so when I say massive, I mean of order, you know, solar mass, right? M solar. And then by small, I mean of order the size of an atom, right? Right. So size of atom, which is like 10 to the minus 15 meters, right? And that, the only thing we really know about, right? And by know, I should put that in quotes, is the center of a black hole, singularity, right? So if you've heard about black holes at all, you probably heard of the word singularity, right? So remember that black holes are an object that um, that has what's called an event horizon around it, right? And that light and nothing can come out of the once it's whatever. If something has passed through the event horizon, it can never come out again, including light. That's why it's called a black hole. But that event horizon is not really a physical thing. It's not like a balloon, and that's the sheath of the balloon. It's just a place um, after which you can't escape. So if I were going to draw a black hole, 2D black hole here, here's the singularity, and here's the event horizon. And this thing is not like the membrane of a balloon, right? It's just a point in space. It's just a point in space. And if you crossed over that, you can't go back out again, right? So you just and in fact, you would end up, you have to hit the singularity if you cross over. That's a black hole. So this thing here, the singularity, has been shrunk by gravity into a very, very small space. And we actually don't know how small, right? Classically, meaning if we don't take any quantum mechanics into account, we think this would be an object with zero size. So it's not that it has any size at all. It has zero size. It's shrunk to zero size and still has, let's say, you know, a solar mass or billions of solar masses, depending on the black hole. As we know, black holes that have billions of solar masses shrunk down to the size of nothing. Um, Now, we don't know for sure what happens here at the singularity because we don't know this. Okay, this massive and small, we don't know. We don't know what happens. Okay, so that's kind of a big blank in what we know, and a lot of people are trying to work on it, and trying to figure out how do you marry general relativity, quantum mechanics, all these things together, right? Um, does that make sense? Sort of. Not
Mhm.
that it would, but it's yeah. This is a real problem because there are real black holes, and we do not understand what happens in there, right? At that singularity, we do not understand. Makes sense, sort of, that we don't understand. It's a lot of people doing a lot of work here. So here we have massive along this, right? So we did massive, and small and fast. These two things here. So basically, this is married to this, really. If you figure out this, you know this. Okay. So these are the unknowns in physics right now. Right? And a lot of people are working hard. String theory is one of the theories that is an attempt to marry these things, in a sense, sort of a theory of everything, like Einstein called it. He didn't know about string theory, but he knew there was something missing, right? He knew that quantum mechanics and general relativity did not play well together, right? That nobody knew how to marry them. And so he called it the theory of everything. And he spent the rest of his life after he, invented special relativity and general relativity, trying to find this theory of everything, and did not come up with it, and no one has so far. So one of those things we don't know yet. Hopefully we will know, right? Anyway, so this is kind of the lay of the land in physics. And oh, I forgot to write down quantum mechanics here. QM, this class, quantum mechanics. Oh, where's your Spanish notebook? Sorry, hold on, my kid. Write neatly. Okay. So this is quantum mechanics, of course. Although I can't spell today. Okay, and this is non-deterministic, right? This is also non-deterministic. Deterministic. Okay, I don't know. I'm messing up my words everywhere. Okay. So, so this topic is again exceedingly important in physics. Been, you know, this theory, right? As you know, theories are something that has a theory in physics, in science, is something that has passed every single test that's ever been thrown at it. And people still test quantum mechanics the same way they still test gravity. If you didn't know that, they still test gravity. You might think like, yeah, well, gravity's just a fact. But scientists honestly never think of anything as a fact, right? So they will tell you if you press them, right? If you press us about what is true, we will hedge our bets, right? We will say, yeah, we think that the general relativistic theory of gravity is true to 99.9999%, but no one will ever say 100 to you, and probably never will. They'll add some nines, right? Because they keep testing general relativity. There are satellites that we have put up in orbit around Earth that are testing general relativity right now, even though this theory came out in like 1911. So same thing with quantum mechanics. Always doing new experiments, always trying to figure out, you know, how quantum mechanics affects this or that system, right? Always testing, always, and that's just the way it is. You know, that's the way science works, right? You don't ever, you're never going to get someone say, well, it's 100% sure, right? I mean, they might say that colloquially, if you know what I mean by that, like in just talking at a party, but there's no such thing as 100% sure, right? So very similar thing with quantum mechanics, always being tested. It's not like it was invented in like 1930 and everyone's, well, we're done with that, you know, move on. Always testing. And also, you know, people, one of the reasons that people test stuff so much, I think, honestly, is that not just because they, you know, really want to, you know, make sure the theory's right. It's hoping that it's not, right? Hoping that they get some really cool, weird answer that's different than what the theory predicts, right? Because if that happens and you didn't make a mistake in your, you know, your experiment, and it leads you to some cool new physics, or even it doesn't lead you to new physics, it's just some weird cool thing, that can lead to things like Nobel Prizes, right? So, for instance, there is the Nobel Prize, I think it was, gosh, I can't remember now. That's bad. I can't remember when the Nobel Prize for this thing was. But back when I was finishing up my grad work, so I graduated in 2000 from Cornell, and there was this group at Berkeley, I think, who had measured the acceleration of the universe expansion. So, you know, you all probably have heard the universe is expanding, right? And they had measured that that expansion was actually accelerating. Like it wasn't like slowing down. So think of an explosion, right? Think of an explosion. Let's imagine an explosion, and you're, you know, let's say you have a, you know, one of those like mines that the people put in the ocean for ships or something, right? To blow up ships. let's say it just blows up. You can think of all the water that's going to spray, right? Well, what's going to happen to that water spray from the explosion? It's going to start slowing down, right? It's not going to accelerate out. Right? It's going to slow down as it gets sprayed out. It's going to be really fast, and then it's going to slow down, right? That's what you kind of expect for the universe, that it's expanding but slowing down, right? And that's not the case that was not the case according to these people from Berkeley, right? They're like, no, it's actually speeding up, which is weird. Like, why would it speed up? I mean, your car doesn't speed up unless you put your foot on the gas, right? If you let your foot off the gas, it's going to roll to a stop eventually, right? So why would it be speeding up? And we still don't know the answer to that question, by the way. But people at Berkeley were like, it's speeding up. I'm sorry. Here's the data, right? And everyone was like, no, that's wrong. Come on, that's not right. Here's all the mistakes you must have made. There was a bunch of people who wrote papers about how their methods must have been wrong, and how that if you tweak this thing in their thing, then you wouldn't get that result. And then another group separately came out with that same thing, and all these papers that were trying to figure out what they had done wrong, just one by one, just that turned out not to be true, right? So they would be like, well, you didn't tweak this thing. And then the authors were like, well, no, if you do it this, if you tweak this other thing, and if we if you tweak this, you're not really taking into account this other thing. And so after years of going back and forth about this, right, nobody could prove that they were wrong, and there was even more data by that time showing that they were correct. And again, this just goes against like everything we know about cosmology, right? So it was the beginning of one of the big mysteries we have, which is dark energy, which is what's causing this acceleration. We don't know what dark energy is. Right? We do not know. But that was the work that received the Nobel Prize. I gotta say it was 2012 or something. Now I can't remember. But again, people look for stuff, like people are doing tests over and over again, and they honestly, in their heart of hearts, don't just want to get what they predicted. I mean, I think it's fun to get what you predict, because it's really amazing that you can write down equations that govern the universe, right? But I think most of them, in their heart of hearts, want to find some really interesting, weird thing, like the universe is accelerating, right? So again, all of these theories that we have, quantum mechanics, general relativity, classical mechanics, are just constantly being tested. And so things I tell you are things that have been tested over and over and over and over again. All right. Just FYI. All right. So let's talk a little bit more about the difference between classical mechanics and quantum mechanics, but let's do it with some equations. And I'm going to get a new layer for this. Okay. So let's look at classical mechanics or classical physics. And here's where your knowledge of differential equations would be useful. I'm glad that Aaron has some differential equations. Let's think about. I'm sorry, Holly, the kid. What?
For Spanish, she just took out one day.
She took out Monday. Okay,
Yeah.
Tuesday?
Yeah.
You did?
No, I just started. I just came back here to tell you there's no more because there's no decision. So just.
All right. Okay. All right. So in classical physics, how do we figure stuff out, right? Well, you all know that in 115 you had equations of motion, like the kinematic equations, right? Like x equal vt, right? Had that. For things that don't have any acceleration, just right. And if it has acceleration, you'd have like x equal 1/2 at squared plus vt plus, right? Those things actually come from the more fundamental equation, which is Newton's second law. Okay, you may not have noticed that at the time, but that's where they come from. And Newton's second law. So I'm just giving an example. Of course, there's many things that go into classical physics, but this is a good example. Newton's second law is actually a differential equation. Okay? So this is a differential equation. And what do I mean by that? Well, you all know the, F equals ma, right? And this is a vector equation. All right, so let's just work in 1D. So in one dimension, I can write, F in the x direction, right? Or, so this would be the net force in the x direction. So net force. And this would be something like if you're doing a problem in physics, you would sum up all the forces in the x direction. That's a net force, right? And is equal to m, and the acceleration in the x direction. So we just stay with one dimension. So this is a differential equation because I'm going to turn it around and I'm going to write ax equals fx over m. But this a, remember, right? A sub x is the derivative of the velocity in the x direction with time. And that v is a derivative of the x of the position with time. So this is actually a second derivative of x, right? The acceleration is the second derivative of x with respect to time, right? So I write that over here, d squared x dt squared is equal to F, the sum of all the forces in the x direction, the net force over the mass, right? This is a differential equation. It's called a differential equation because it has derivatives in it, right? This one is a second order, ordinary because it doesn't have any partial derivatives, ordinary differential equation. And it's second order because it has a second derivative here. The highest derivative is a second derivative. So if the highest derivative was a third derivative, it would be a third order, okay? All right, so second order differential equation. And in a particular situation, you might have different, you might have different forces, right? This is not the most fundamental version of Newton's equation because the most fundamental version is another differential equation that looks like this, dp dt, where p is the momentum, let's just use it in the x direction, is equal to the sum of forces, right? So this is actually the exact same equation, except for the m, right, that p sub x is mv sub x, right? The momentum. So this is actually even more fundamental here. And this is written as, you can see, a first order, still ordinary. It's the same as this, except for this accounts for, DE here. I'm going to put differential equation, DE. So this thing here is the same as this, right? It's just that it allows for the fact that M might be changing, like when you have a rocket, right? Rockets are expelling fuel to give themselves thrust, and that fuel is changing their mass because they're getting rid of the fuel, right? Very, very fast. So that change in mass matters for a rocket. Okay, but anyway, these are differential equations. All right, so let's just take a look at one of the differential equations. I'm going to take a look at this one. They're the same, but I'm just going to use this version. So I have d squared x dt squared. And this is equal to the net force over m. And now I'm going to say what net force, let's just pick one. Let's pick a net force that we want to use for our example. So let's use the force of gravity. Okay. So in this case, right, the force in the x direction, let's say, And let's just make x be down. So that'll be just easiest. So I'm not going to change variables to y or anything silly like that. And we're going to have this be the negative direction down. So we're going to have this is going to be minus mg, right? Where g is acceleration due to gravity. And so here, this becomes minus mg over m, or minus g. Okay? So now our differential equation looks like d squared x dt squared is equal to minus g. Okay, notice they have the same units, right? This is in meters per second squared, x is in meters, t is in seconds. Oh, sorry, yeah, in seconds. So this would be meters per second squared again, right? So the units all work out here good. This is a differential equation that we can solve. G is just a constant, right? So this is just G equals, 9.8 meters per second squared. And so this is not changing with time or with x. So what we can do is we can integrate both sides, right? So we can say, okay, I'm going to do an integral over time. So I'm going to integrate, I'm actually going to change this. So I know that d squared x dt squared, I can write as just the time derivative of the velocity in the x direction. Remember, x is down, right? And that's equal to minus g. And so I can integrate both sides over time. If I do it to one side, I can do the other side, right? So notice over here that I cancel out these dt's, and by fundamental theorem of calculus, I can just write this as v sub x. And on this side, I just get minus gt plus some integration constant, yeah? Okay, now let's do it again. So I know that vx is the derivative of x with respect to t, sorry. And now it's gt plus c. C is constant. I'm going to integrate again over time. And so on this side, again, we cancel out those dt's and we get dx. I'm sorry. Why did I write dx? We get x, position, is equal to, this one here gives me minus gt squared over 2, right? Because the integral of t dt is t squared over 2. And then plus c, oops, there's an integral here that I forgot here. Plus c times t, and then plus another constant, c prime. All right, let's write that up here. So we have now x equal minus g t squared over 2 plus ct plus c prime. I hope this is looking familiar, right? Okay. And let's think about these c's. Well, this differential equation is really not done. And if someone didn't give me initial conditions for this, right? If I didn't have any initial conditions, I wouldn't be able to do anything with this. So let's think about a situation, right? Someone tells you, I want to drop a ball off the top of a building, right? Okay, and you'd be like, well, yeah, this is the equation because g is constant, like the acceleration, right? The force of gravity is constant. And this is the equation. I just solved the differential equation for you, and here it is. Okay. Could I use this equation to tell them where their ball is going to be at all time? What do you think?
Yes.
How? Tell me what I would do. Say they want to know where their ball is at t equals 2 seconds. What do I do?
You would just plug in the for t.
Okay, so x equal minus g, and 2 squared is is 4. So we have 4 seconds squared over 2 and times g, which I'm just going to make that 10 in a second, plus c times 2 seconds plus c prime. So I got g is, let's just make it g10 for just fun. Okay. So this becomes minus 20 meters, right? Because the second squared cancels with the g second squared. Plus 2 times 2 seconds times c plus c prime. Does the person who wants to know where their ball is know where their ball is?
Oh no, because you still have the C's.
Right. So differential equations are not the end of the story. Differential equations have to have either initial conditions when the derivative is with respect to time, or what's called boundary conditions when the derivatives are with respect to position, which we haven't seen yet. Okay, so without those, they're not useful, right? So you have to have the initial conditions, and in fact, you have to have 2. And the reason you have to have 2 is because this is a second order equation. If it was a first order equation, you'd only have to have 1. If it was a third order equation, you'd have to have 3. Okay, so what are our initial conditions do you think would be useful for a problem like this? What would they be? And what do I mean by initial conditions anyway? What do I mean by that? Does no one know what those are? What is an initial condition? When I say that, what do I mean?
Oh, like for example, if you're dropping the ball from a certain height, that's where it will initially be starting
Yes.
or something like that.
Yeah, right. Okay, so let's say my friend says, oh yeah, I want to know when there is a 2 seconds and I want to start my ball out at x equal, 5 meters. I'm going to drop it from 5 meters. Okay, good. All right, well, let's see if we can get somewhere then, right? So let's go back up to here, and that's going to be at t equals 0, right? The 5 meters, it's at t equals 0. Okay, so he tells me at t equals 0, it's at 5 meters that I drop at, and I want to know where it is 2 seconds later. Okay. So let's see what we can do. So we know that x equals 5 meters, so we're going to put the 5 in for the x when t equals 0. So this term will go away. So we got a 0 there. This term goes away, 0. And then the c prime sticks around. So that tells me that c prime is 5 meters. So good. Now we can rewrite our equation. X equal minus gt squared over 2 plus ct plus 5 meters. Now can I tell him where his ball is at 2 seconds?
No.
No, because I still got a c. So
So
what
would that be velocity?
Yeah, let's use velocity. So v, let's say v equals 0 at t equals 0. So he drops it from rest. Sound good? All right, let's go here and see about that. Okay, let's wait a minute, we can't do that, right? We don't have any v's in this equation. What should we do?
Now that you have, well, mm, mm.
What can I do to X to get V? No ideas?
I'm blanking right now.
So let me ask you this. If this is X, and this is T, and this is, the position. I'm not drawing for our particular situation. I'm just drawing a general, X versus T. How would I get V from this graph? Maybe I can make it easier. What about if this was X versus T?
V would just be the rate, the price overrun.
That's right, the slope. Same thing here, except for now the slope changes, right? Here's the slope here. Here's the slope here. Here's the slope here. Here's the slope here. Here's the slope here, right? And how do we get the slope of something that's changing like that? Like, can't just use rise of the run. What do we do? Hint, it's from calculus. All right, well, let's back up to here. Let's go to the line. And you said it was rise over run, right? So that would be like delta x over delta t, right?
Mhm.
What does that remind you of from calculus? This starts with a d, right? Delta?
Yes, your derivative.
Yes. So, right, we go to calculus, we take the derivative to get the slope. Right? That's the whole point of calculus in some sense is this, right? Is getting the slope of something that changes, that you can't just do rise over the run, right? You use a derivative, right? And we know that v is equal to the derivative of x with respect to time. So let's just take the derivative. So dx dt. Over here we'll have 2 times minus g times t, and that'll cancel that too. So I'm just going to get minus gt. Here the derivative is just c, and the derivative of the 5 is 0. Yeah?
Mhm.
Okay, and you can see we actually have that here. This is the v. I'll just write vx equals this. We have it here already down here. Because when we integrated, we got that first. But anyway, okay, so here we go. But it's very common in a differential equations that you solve for your variable, and then you have to take a derivative to, to get to the next level of something that you need. Okay, so let's now do what we were going to do. So we know that the v is 0 at t equals 0. So the t equals 0 part here will be just 0. 0 equals c, right? So that means that this c is 0. So my final equation is x equal minus g t squared over 2 plus 5 meters. And now we can tell the person where it's going to be at 2 seconds, right? We know that we had that minus 20 from when we substituted in the 2 seconds here. So we get minus 20 meters plus 5 meters, and we get that's minus 15 meters. That is where that, whatever it is they're dropping, is going to be, right, at t equal 2 seconds. Right, so for instance, if that 5 meters is just 5 meters above a cliff, and they're dropping it off the cliff, it'll be 20 meters below the cliff at 2 seconds. Yeah? So notice that we took Newton's second law, and we just said, we're going to have a force, and that force is going to be the force of gravity, right? And then we were able to get to a point here where we have a solution to the differential equation, but it's not complete until you have the correct number of initial conditions. And this is true for all differential equations. So differential equations have to have either initial conditions or boundary conditions, and we'll see what those are in a little bit. Otherwise, they're not complete and you can't use them for anything. You can get the form of what they're going to look like, the solution for x, right? In a differential equation like this, you're solving for x is what you're after. You're after x, right? As a function of t. T's down here. Right? So this really I could write as x of t, right? But it's not complete without those boundary conditions or initial conditions, because you can't get the answer that for somebody, right? Okay. And you're going to see that similar thing happening in quantum mechanics, except for we're going to have boundary conditions instead of initial conditions most of the time. And boundary conditions are just means I need to know the value of the function, whatever it is I'm solving for, at certain places in space. And if I have a second order differential equation, I need to have 2 boundary conditions. If I have a third order differential equation, I need 3 boundary conditions, right? Three specified functional values. Kind of like our initial conditions. What is x and what is v at t equals 0, right? Okay, well, I think our class is over at 10:40, right, guys? Yeah. Okay. Well, we'll see you on Thursday, and we won't have any homework for a little bit. Oh, and Moodle page is where everything's going to be, like, the videos will be uploaded. I mean, they're going to be, like, they're going to be YouTube links, but that link will be on the Moodle page. Okay?
Mm-hmm.
All right, guys. Bye.
Bye. Thank you.
All right, see ya.